So anyway, everybody is welcome, and I think we can just start. So, of course, we have a lot of things to cover, but there won't be any point covering them unless we really understand special relativity, which I'm sure in some form you have all learnt, but I would like to revise it for a couple of lectures with your permission, actually even without your permission. So, the reason is that when it's taught first time, it is taught in a certain way, which is very useful. There are a lot of physics of people moving and clocks and fireworks and all kind of strange things happening. But now we need to also make it little formal, because general relativity, which is the main subject of this course, is quite a formal subject. This is not supposed to be a formal course, but even when you teach it informally, it's still quite a formal subject. So to write any expressions and equations, we'll need some formalism. So we'll try to derive that, and we'll start with special relativity. One more thing is that special relativity gets built up over a lot of discussion, and sometimes that discussion may obscure the very simple concepts behind it. So I would like to use this class and the next one to emphasize the very essential simplicity. Also, I'm not sure how many people appreciate that basically one experiment and one theory which existed before Einstein came on the scene were responsible for special relativity to be formulated in 1905. The experiment, I'm sure you have heard, is the Michelson-Morley experiment, and the theory was Maxwell's equations. But again, you shouldn't think of Maxwell's equations as a theory. They were built up from a lot of experiments. So everything, the content of these two things is all built up from experiments. Those experiments could have gone a different way. It's quite a striking fact of history that they went in the direction they did and gave us the results they did. And because they are experiments and they were repeated by other people, they are true, and so these are true facts, not just some hypothesis. And although the books are full of how Einstein used to travel by tram and dream about elongated length contraction and time dilation, basically his paper starts by saying, look what this experiment is saying, it must be true, therefore what can we do? Okay, very important lesson. Okay, so let's quickly summarize what was known before Einstein, or before this work. So there was a concept, it was formulated actually by Galileo among others, called the universality of laws of physics, which basically said, look, it's not much use if the laws of physics are only true in this classroom, and then other laws of physics are true in the next classroom, and in some other ICER, some other laws of physics are true, and in between no laws of physics are true. This is not a useful thing. This is not the goal of physics, and this is also not what we experience. We experience that if we travel to another country, the culture may be different, but the way things move and the way friction works or gravity works or various things work looks pretty much the same. We then extrapolate that this should be also true on different planets, which is a bigger extrapolation, and then to even different galaxies and everywhere. Galileo made the comment, as I understand, that if we are closed inside a ship, so at that time I suppose there weren't trains, or not, at least not that I know of, but there were ships, and if you are closed inside a ship without any way to see outside, and if the sea is very smooth and it's not bumpy, then you would not actually know that you are not on land if the ship is moving at a uniform speed. And this is a principle which became known as Galilean relativity. Now, Galilean relativity means that the laws of physics should be the same in all frames that are moving with a constant velocity with respect to each other. And indeed, Newton's laws satisfy that. property, which I'll just show you in a minute. But obviously, this doesn't mean that the measurement of your position will be exactly the same if you are moving in a ship or stationary on land, because the ship is actually moving. So the person who is stationary in the ship cannot also be stationary on the land, from the land point of view. So if somebody is watching the ship through binoculars, that person who's on the ship and stationary will of course be moving with that ship from the point of view of land. So some transformation has to be made. The claim is, universality claim is, that that transformation is enough to map the laws of physics on the land to the laws of physics on the ship. And what is the transformation? It's extremely simple. We simplify our life to one dimension. It is just this. And these are called Galilean transformations. So the fact that x prime, x in the new frame, is x minus vt, where v is the velocity of that frame with respect to the other one. The fact that x prime is not the same as x is exactly the fact that a stationary observer in one frame will be moving in another frame. Okay? So in this picture, I imagine that v is the velocity of a ship relative to land, and x is the position of the person on the ship. X prime is what I see from the land. Sorry, wrong way. This was not right. This is the velocity of the new frame. This is the position in the new frame. Okay, and good. And since in the new frame, which is the ship frame, I'm moving, but I'm stationary in the ship, so my x prime can be, say, fixed at 0. The person on land will see that my x is equal to vt, which means I'm linearly moving in time as the ship moves. So that's it. Nobody actually thought of questioning this second one, because it was obvious that time is always the same no matter for who it is. That turns out to be false, and in special relativity and in general relativity it's disastrously false. We actually don't have any idea what time means in general relativity. Okay, I exaggerated. We have some idea, not a very, it's very, very confusing. It's like the worst problem in general relativity is to understand time. And this messes up all of physics, because all of physics is concerned with time evolution of something. Okay, but it's very scary when we don't actually understand time, but these people thought they did, and so they said t prime is t and this is this. Now this is very good, and immediately from this we can derive a consequence. Let's look at Newton's laws. So Newton said that in the absence of force, mx double dot equals 0. Okay, and let's ask, if this is true, then what can we say about mx double dot prime, where x prime is this. Dot, I hope you know, means d by dt. So double dot is d2 by dt squared. So what is this? Well, it's d2 by, first let's go slowly. X dot prime is the dot of this equation. So there's x dot, and dot of t is 1, and v is constant, so its dot is 0. So this gives me x dot minus v. So far this is a nice equation. It says that the velocity in one frame is the velocity in another frame minus the velocity of the motion of one frame relative to the other. So this is very good. Differentiate once more and you get a nice fact that the acceleration is the same in both frames. Remember, we have assumed the velocity of different frames is constant, and we'll have to keep assuming that, because that's all we know to do here as well as in special relativity. If we want to go beyond that, we have to go to general relativity, and guess what? You have come to the right place to learn that in some time. But for a while, we will be constant. We'll only consider movement between constant frames moving with constant speed. So this universality is limited only to such families of frames. Okay, so this is true, and therefore, if this was true, then mx double dot prime is also 0. So there's no acceleration for a body in a moving frame if there was no acceleration on that body in the stationary frame. So Newton's laws, we have just transformed them from one frame to the other, unprimed to prime, and they are the same. That's very nice. Okay, so this is compatible with that. If that breaks down, this breaks down, and vice versa. If we change that, it may not be compatible with these transformations. If we change these, they will not be compatible with Newton's laws. Good. So that's the first observation. A second observation, I'm sure you remember this formula, so I can keep using it. I can erase it now. Second observation is, and it's a very useful one, is let me consider, so now I'll give a name to a frame. F will be a frame, always assumed to be inertial, F prime another one, and F double prime a third one. And the notation will be straightforward, that in F, the coordinates of space and time are x and t. Here they are x prime and t for the moment, and here they are x double prime and t. T never changes in Galilean relativity, but x changes to x prime when one frame moves relative to another. Then if I go from that frame to another one, so I could have, for example, a ship moving relative to land, and in the ship I can get on roller skates and be skating along the ship. Okay, so my velocity on the ship might be v2, the velocity of the ship might be v1. So we'll assume that the relative velocity of these frames, between these two the velocity is v1, and between these two the velocity is v2. That means this moves at v1 relative to this, and this moves at v2 relative to that. Okay, now let's compose that. So now supposing I'm roller skating on the ship, then I want to know what is my position relative to the observer on land. I just ignore the ship part completely. It's just me. I'm just focusing on myself. So of course what I'll say is that x prime double prime is x prime minus v2 t. This is the relation between me and the ship, and then this is equal to x minus v1t minus v2t. So this part x prime is x minus v1t. So I compose that, so I just collect terms and I get this. Okay, no surprise, I added two velocities and I got v1 plus v2. That's what we are taught is the meaning of addition. Turns out life doesn't actually satisfy this rule, and you can see why. If I take v1 and v2 to be some large velocities and add them, I'll get a larger velocity, and there's no limit. I can just keep considering frames which move with respect to other frames, and ultimately this shows that there's no limit on the upper limit on the velocity. I can have any velocity I want in principle. In practice it might be difficult, but by this means I can generate any velocity. Okay, there cannot be a barrier, so velocity is unbounded above. If there's anything unclear, please do ask. Remember, you can't suddenly invent some rule which says no, I won't allow velocities above something, because we are allowed to change frames by Galilean relativity, and when we do that we get this result. So if you invent some barrier, you say there's some speed capital V that I can't go above it, I can take this to be 2/3 of that capital V, that is allowed. I can also take this to be 2/3 of that capital V. Sum of it will be 4/3 capital V, and it's above my limit. So I can't place any limit. So in this system I can't have an upper limit on the speed of anything. Very important fact. Okay. And the last observation, which was considered obvious until Einstein really unraveled it, was that since t prime equals t, there is a universal concept of what it means that two things are simultaneous. So it's called simultaneity. That means if two things happen at the same time in one frame, they will happen at the same time in another frame. Okay, it was obvious. People didn't dispute that possibility. Okay, there was nothing to dispute in that. Is it clear what I mean by this? let's say there are two firecrackers on the ship. Unfortunately, since we have to have something dramatic happen, usually there are firecrackers, which are probably not allowed on ships usually. But in this case, two firecrackers at different places on the ship, and they are timed according to a clock to explode together. Okay, the person on the land viewing this ship go by will also see them explode together. That's it. Okay. So these are all features of Galilean relativity, and now let's see why it unraveled. So there are two things that made it unravel, and I mentioned them already. The Michelson-Morley experiment and Maxwell's equations. So we'll come back to Maxwell's equations later, maybe next time. But this experiment, I'm sure you know how it works. There's some mirror setup. You send a beam from here. This is a partially silvered mirror, so the beam can go here and it can also go here. So there will be a beam, but these are proper mirrors. So the beam comes back from here, and at least some part of it will come here, which is my detector. And here the beam which continues straight will also come back here, and some part of it will also come to my detector. So I'll have two different beams reaching my detector, one which has followed the trajectory this to this to this to this, and the other this to this to that to that to this. So two different, they have traversed different lengths. Now the question they wanted to understand is what happens to the speed of light. Now I'm not going to derive those formulae again. That's something I hope you have done, and if you haven't, you really should do it. In fact, a year ago I think I gave a project to some math students where I asked them to read these people's paper, Michelson and Morley's paper. You can also download it and read it. It's fun, and it explains everything. Also, by the way, Michelson made a calculational error in his calculation of the path length, but it got corrected by other people. So anyway, you do this. Now the key point is simply this, that the light is traveling, all the light is traveling the same way up to this silvered mirror. After that, this is doing that, while this one is doing that. And then after here, again, they are both traveling a common path. So the difference, if any, is between the time it took to do this and the time it took to do that. Okay. Now, there are two things. One is you can do the experiment at different times of year, which is what they did. They did it twice a year. And the Earth is going around the Sun. So at different times, it's oriented differently towards whatever frame we might have imagined the light is fixed in, okay, or the light is propagating in. That's basically the idea of a medium in which light propagates. So it can't be that, it must be that some time of the year, this one goes against the medium and this one goes parallel to the medium, or this one goes perpendicular, this goes parallel. Moreover, I think the experiment could be rotated itself. So in the same time also, I can just rotate by 90 degrees. So if the movement of a medium is in any way affecting the speed of light, is bound to be picked up, because in this direction, the light will be affected by the movement of the medium through which the Earth is passing, and in this direction it won't. We don't know what is this direction. We don't know what is the direction of the medium when we do this experiment, but we simply say that, look, it can't be that this one and this relative, see, these lengths need not be the same. That nobody wants to make the experiment so precise that these lengths are exactly the same. The point is that when these beams come, they interfere, and when I rotate the apparatus, those fringes should shift. That's all. Or when I keep the apparatus fixed and I let the Earth rotate the apparatus by simply moving around the Sun, again the fringes should shift, and no fringe shift was found. In some units, I believe they said something like 0.4 fringe shift was expected. By any estimate of, you can estimate the velocity of the Earth and so on, those things. And the bound they found was below 0.02. So a very good experimental bound. So fringe shift expected I suppose they meant 0.4 of a fringe. That's pretty big, right? It means that the bright fringe has gone more or less over where the dark fringe was before, and found less than 0.02. There are always errors, but this is pretty dramatic, especially for those times. And so conclusion was speed of light just doesn't change. Now when speed of light just doesn't change, that itself is the end of Galilean relativity. Can't be, the speed of anything cannot refuse to change when I change frame in Galilean relativity. So speed of light is constant, independent of the frame, end of Galilean relativity. In fact, if you think very hard about Galilean relativity, it even tells you that if I could move in the medium at the speed of light, then relative to me, light would have come to rest. Okay, because I can take any V1 and V2. So if V1 is C and V2 is minus C, then for me, light would come to rest. Of course, this was not a puzzle for experimenters at the time, because we obviously can't move at the speed of light or even close to it, so it's not something we can test. So people might have said, well, who knows, maybe when we do learn to move at the speed of light, it will be found to be at rest. But this experiment showed that isn't what's happening. Galilean relativity itself is wrong. It's not a practical conclusion that this is what we can understand. It's an in principle conclusion that these rules cannot be true. Okay, good. So what is true? That's not difficult to find out. Okay, the second thing I was going to say about Maxwell's equations can also be said now. Maxwell's equations contain a parameter C. How are they, which is the speed of light? How are they supposed to be true in all frames if the speed of light isn't the same in all frames? That's one more reason to kill Galilean relativity, even without doing this Michelson-Morley's experiment. Because the equations have a fixed C, but if we believe in universal equations that are the same in different frames, they can't be right. But of course, you could have argued somehow that maybe C is only the speed of light on Earth, and we are on Earth. You know, we had not done space travel, we had even not done flight of the Earth. Everybody doing physics was anchored to the Earth. So they could argue that, well, Maxwell equation only describes the Earth. But if we really believe in universality of laws, it raises a puzzle. So these are the two paradoxes which said this can't be right. But this one gave a way to find out what is right. Actually, Maxwell's equations also give a way to find out what's right, but it's a slightly more complicated way because it involves electric and magnetic fields. This doesn't involve any fields, it just involves position and time. So let's do this. Okay, so what does this tell us? This says that dx by dt is equal to c, which is constant. Now taking this magnitude is a bit inconvenient, so it's better to just square this, and this is still true. Here we have, it's a vector and we have squared it, taken its dot product with itself. So this equation is still true. So we have, if light moves, if light moves a distance, small distance, dt in dx in time dt, then we can use this equation to bring dt squared to the other side, and we get minus c squared dt squared plus x squared plus y squared plus z squared equals 0. D of everything. Yeah, thank you. Now you may wonder why I'm using this dx dy. Why not just use finite intervals? since c is constant, this equation is also true for finite intervals. You can just put t in place of dt and x, y, z in place of these, and it will be true. But you should get used to this notation, because we'll soon be working with systems where the invariant quantity, the quantity which remains unchanged across frames, is not writable in a finite distance form. It can only be written in terms of infinitesimal distances. So the whole of general relativity has equations written in this form. So we'll just work in this way. Both are true. In this case, the infinitesimal form and the finite form. But in general, they won't be. Okay, so this is 0. And now our job is to find a set of transformations to a new frame where the coordinates are not x, y, z, but x prime, y prime, z prime, such that this is still true in the new frame. And the first thing you can see is that if I do that, I can, well, so I didn't mention this earlier, but we have been talking of frames which move relative to other frames, but we could also think of a frame that rotates relative to the original frame. It doesn't move anywhere, it just rotates. Now you can see from this equation that this quantity is invariant under rotation. This is nothing but what we call dr squared, where r is the radial vector, and so it's completely unchanged by rotation. Okay. But what about translation when the ship moves with velocity v? There's not much hope to get this whole thing to remain 0 unless t also transforms. You can see that. Because if I translate, for example, I can just ignore these. I can just consider light propagating in the x direction. Now, there isn't any linear transformation of x other than a constant shift, which is going to keep this whole thing invariant. So, we'll have to allow transformation of t with x. So, we have to just allow it. If the equation says it's needed, it will be needed, and we'll find it out. We are just discovering things. We are not assuming any laws, except the law that the speed of light is constant in all frames. So what are we going to do? Well, what we are going to say is that let x prime be equal to ax plus b t, and t prime equals cx plus d t, where a, b, c, d are constants. So this is called a linear transformation, and it's the most general linear transformation between coordinates x and t and coordinates x prime and t prime. Okay. Now this form of what I've written, so now we have to find out a, b, c and d, such that this quantity without these terms, if it was 0 in the x and t frame, should remain 0 in the x prime and t prime frame. And it's a very easy exercise in principle, because then I have to just write down minus c squared dt prime squared plus dx prime squared, which should be 0 because of the assumption that speed of light is always the same. And then I have to calculate this in terms of a, b, c, d and x and t, and in the final answer this should turn into minus c squared dt squared plus dx squared, and this will put constraints on a, b, c and d. Okay, so the project is clear. Now one very inconvenient thing here is that x has dimensions of length and t has dimensions of time. So a will be dimensionless, d will also be dimensionless, but c and b will have dimensions, which is really annoying. We can solve that by, in fact, since there's a constant in our problem, we can just redefine this transformation by putting c in front of t everywhere it occurs. What does that do? It's just a new way to define time. What does it actually mean? If t is the time taken for a process, then ct is the distance that light has traveled during that time.
Maybe you don't want to go to C.
Maybe I don't want.
By C in the first one.
Oh yeah, sorry. Here I didn't want it. Thank you. Please keep pointing out my typos. There will be many. Yeah, obviously I don't want it there. With this choice, A, B, C, D are completely dimensionless because everything in this equation has dimensions of length. Okay, but I did see people puzzled about the use of CT. So if you have any question, please ask. If you like me to repeat why we use CT, I will tell you. You might have heard of the concept, well, there's an inverse concept which people also use, which is using x upon c as a time. I mean, you can also do it that way. So light year, you must have heard of the concept of light year, which is commonly used. Okay, actually it's the same concept. So if t shifts by 1 year, then ct is a quantity with dimension of length which shifts by some amount, and that amount of distance is called a light year. So light year is not a measure of time but of distance. Okay, it's a huge distance. Why do we use light years? Because astronomy requires us to consider huge distances, because other stars and galaxies and so on are huge distances away. So if we measure in centimeters, it will be a nightmare, and if we measure in kilometers, it's still a nightmare. Okay, in light years it's better, even that's not great, we have other units, but this is what basically it means to multiply t with c. You get a unit of length to measure time. Yes?
Why linear transformation only?
Good, thank you. So we are assuming a linear transformation because it's pretty unlikely that a non-linear transformation would preserve something like this. This is a quadratic form. Okay, and it's if I just imagine if I had some non-linear term, for example x prime had x squared in it. Okay, you can try it. You can just allow a, b, c, d to be functions of x and t if you want. Okay, certainly this is not going to be invariant. You can easily see that. There's no chance. I'll give you an example. Supposing x prime has a times x squared. That's a non-linear one. Okay, so what is dx prime? It's x dx, 2x dx. So you'll get 2x dx whole squared here. This is not good. Okay, this is a very simple quadratic form with constant coefficients. So its symmetries will be those of linear transformations of these variables. In fact, the calculation is not that different as working out how dx squared plus dy squared remains unchanged under rotations. It's the same story, but except there's a minus sign in front of time. If you think of dx squared plus dy squared as an element of length in a plane, and now I allow myself to rotate, what is the rotation? It's just a linear transformation of x and y to x prime and y prime. Okay, I can't make a non-linear transformation of x and y to x prime and y prime and have that radius vector remain constant. It's the same reason. It's the same calculation but for a minus sign, and actually many things in relativity are like that, but the physics is completely different. Time and space absolutely don't have the same meaning. Okay, but the mathematics somehow makes use of time having a negative sign in this invariant quantity. That is somehow central in the subject.
So if we assume the transformation to be non-linear, do you think it might not play well with the assumptions of homogeneity of space? And
yeah, there are many things it won't play well with. I agree with you, but I think right now we are taking the narrow question of what preserves this element.
Right.
This is called a line element. It's actually square of a line element. So its square root is called some invariant distance in relativity, because it's exactly the thing which has to remain unchanged when I go from one inertial frame to another. Okay, so it's a simple element, line element, and it should just remain unchanged. Yes?
What motivates you to say that it should be invariant?
Invariant. Oh, Michelson-Morley experiment.
Okay, and something
Because the speed of light should be the same, and the speed of light being c is what gives me this equation.
is there something else, like some quantities or some symmetries which will not be there if I don't take it?
Yeah, I don't assume anything except that speed of light is fixed. You see what will happen. This equation is always true when speed of light is c in that frame. But if I had two frames, in general, I would think that this goes into minus c prime squared dt prime squared plus dx prime squared. This would be the new expression for speed of light. C prime would be the new speed of light in some other frame, and then this thing would have to be 0. This being 0 is just the statement that that's the speed of light. It's 0 for light, not for everything. Do you understand? I got this by this equation. This equation I hope you accept. Dx dt is c. That's what speed of light actually means. Yeah. So I squared it and then rearranged terms to get this form. Now if I'm in the prime frame, I should take this with all primes and use C prime here, and I get this. So there is no content in the fact that these two are true statements in general, because I don't know what is C prime as a function of C. But Michelson and Morley told me what is C prime as a function of C. It's the same as C. There is no prime. It's the same in this other frame. Now I have a problem which just involves the coordinates. It doesn't involve C really. C is a constant in the equation, but the problem is how to go from x prime and t prime to x and t without going from C to some new value C prime. Yes, question. So yes.
So we started with the initial statement that A by d squared is C squared.
Yes.
That is for objects which are light like.
Yes, yes. Everything is for light-like. This is 0 for only for light-like
Yeah,
things.
so
Yes.
the basis on which we are saying that this expression is a general invariant is just because of symmetry. Is it?
No, we don't. We aren't allowed to assume any symmetry. Einstein was not assuming symmetry. He derived a symmetry from this fact.
No, no, like, for now we assume that for two frames this would be an invariant.
Yes.
They are light like.
Yes.
So
We will come to other things later. I'm not discussing movement of anything except light for now.
of only
Light, only light. But of course, once we find these transformations, it's hard to see that this transformation. This transformation is between two frames. They are not moving at speed of light with respect to each other. This is a property of speed of light in different frames which are related by a velocity v. That I haven't changed at all. Okay, I'm looking at the motion of light, but the two frames I'm looking at are ground and ship. V can even be very quite small. I'm not saying V is equal to C. V is there in the problem. Okay, A, B, C, D, I have to depend on V, because if V is 0, what should I find? X prime and T prime is same as X and T. So if V is 0, A should be 1, D should be 1, B should be 0, C should be 0. Okay, but I'm always assuming that this quantity is exactly 0 for light. So don't mix up these two things. One is the change of frame, the other is the fact that this quantity is invariant because it tells me the speed of the object. This would be true for any object, you see. This quantity is 0 with a v over here, or a v1 or some other velocity for any object. But then the same quantity here will have a different v. We know that the speed of different objects is different in different frames. Okay, no miracle can come out of knowing that, because we don't in principle know what is v prime in terms of v. But in the case of C, the experiment told us that it's the same. This is very drastic result. Okay, therefore these two things must be the same with the same C. That is the fundamental concept of special relativity. And as I told you earlier, Einstein basically said these guys have proved from the experiment that C is the same in all frames. Let's just agree with them. Let's not keep trying to fight what they have found. Many people were trying to say no, but maybe ether is somehow dragging along the surface of the earth and all that. Einstein said no, let's take them seriously. Then this and this have to both be true, therefore that has to be true. No options, yes. Okay, and now we can implement this and find out what are these A, B, C and D. And if we do it, it's a very simple calculation, which I won't do. I want you to do it for yourself, and you'll find d squared minus b squared is equal to 1, a squared minus c squared is equal to 1, and ab minus cd is equal to 0. Three conditions. How do we get three conditions? That's easy to see. Look at this quantity. T prime is a linear combination of x and t. This is also a linear combination of x and t. When I insert those equations in this, I'll get terms with dt squared. Those have to have the coefficient minus c squared. I'll get a term with dx squared that has to have the coefficient 1. And I'll get a cross term also, because I'm taking dt prime to be a sum of things, and when I square I'll get a cross term. So I have two cross terms, but they have to cancel out at the end because the original expression has no cross terms. Okay, so no cross terms is this last equation, and these first two equations are the statement that coefficient of dt squared is minus c squared and coefficient of dx squared is 1. Simple linear algebra, nothing more. Okay, clear? Okay, now very nice consequence of this. We had introduced 4 parameters because of our ignorance. Because we don't know how 2 frames transform. But we have got 3 constraints on 4 parameters. How many does that leave? How many free parameters should there be? 1. And what do we think will be the physical meaning of that parameter?
Something related to velocity.
Exactly. It has to be related to the velocity, because that I don't know. Velocity of one frame relative to the other, not the velocity of light. X and x prime are in 2 different frames. Those frames by assumption are moving with a uniform velocity v. So after solving all this, the quantities a, b, c, d can only depend on one parameter, and that must be the physical parameter v. This is some mathematical thing we did to make the speed of light be the same in both frames, and now we have to do the physical interpretation of this. Now this system of equations mathematicians will quite enjoy, but we don't have to take a mathematical approach. We'll simply, well, we actually do have to take a slightly mathematical approach. So it's a clever idea. You see, you can now take this and ask a mathematician the problem. I have 4 real variables, so they span a 4D space. In that 4D space, I have 3 equations. Each of them defines a curve in that space. What is the common intersection of all the curves? And you have all taken basic algebra and calculus, so you know these concepts, I'm pretty sure. Okay, but we can short circuit that if we have a very good friend who says, look, this kind of equation suspiciously looks like the equation relating the hyperbolic sine and cos functions. Do you know these functions? Sine hyperbolic and cos hyperbolic? Let's remind ourselves of them. Sine hyperbolic of theta is half e to the theta minus theta. I'm sure you know the exponential function anyway. And cos hyperbolic of theta is half the sum. It's nothing but the relation between sine and cos and exponential, but except the I is not there, and so you get sine hyperbolic and cos hyperbolic, or sinh and cos as they're sometimes called. Is anyone quite unfamiliar with these functions? Do tell me, I can go slower if needed. If you are familiar, all the better. Have you encountered them somewhere?
Yes.
People are nodding. Now look, people who are not comfortable should tell me. If you don't tell me, or if you don't tell me now, at least come and talk to me about it, okay? Because I will assume what I know about your first and second year syllabus at least over here. Good. So this satisfies a very nice relation that for any theta, this is equal to 1. I'm sure you know that in trigonometry cos squared plus sine squared is 1. So by going from the usual sine and cos to sinh and cos, you end up with an extra minus sign and you get this. And this looks very much like both of those relations. Okay. Now, of course, it may not be that we can satisfy both of them with the same theta, but we'll take a guess and see if it works. So let A be cos theta and B be minus sin sinh theta, C equals minus sinh theta, and D equals cos theta. So now with these things, is the first line true? D squared minus B squared is 1, and A squared minus C squared is also 1. You may ask why I took the minus, just it's convenient. You can take plus if you like, but this is more convenient. So we've got this, and now the point is the last equation has to be true, otherwise we are sunk, otherwise this method doesn't work. But it seems that it's automatically true because AB is minus sinh cos and CD is also minus sinh cos. They are the same, therefore one minus the other is 0. So we are done. So we have actually solved our problem of getting 4 parameters into one parameter by making this kind of guess. But once we have made it, it's unique because there is only one parameter in the problem, and this is one way to see that parameter. Okay, now you may say very nice, but what does this theta have to do with velocity? It's supposed to be related to velocity, and it's not trivial how it's related to velocity. So let's try to Understand? And for this we start by using a very simple principle, which is that at very sufficiently slow speeds, so if v is much less than c, then these transformations, which we just wrote down, should reduce to the Galilean one. Very important principle of physics is being used here. How did people survive till the 20th century without knowing relativity? Simply because their v was much less than c and their equations were working fine. Okay, so this should happen, and if you see x prime is equal to ax plus b ct, so a is cos theta, so cos theta x minus sinh theta ct, and this should be equal to x minus vt, in only for v small. For v sufficiently small, this should be true. And now we are in good shape, because we can assume, so v is small, but also theta should be taken to some limit for this to be true, right? Because it's a small transformation, and it's clear that theta should also be taken small, because I told you that when theta is 0, oh, this is me. I'm so sorry. I was going to scold somebody. This is me to wind up in 5 minutes, and we are done actually. Good. So, yeah, very good. So, to compare these, we take theta less than 1, and we have a very nice fact that these are cosh of theta goes like 1 minus, or maybe 1 plus theta squared by 2, and sinh of theta goes like theta plus some terms of order theta cubed. If you study these functions, you'll see this is an even function and this is its expansion. And so for very small theta, this is 1 and this is theta. Okay? So with that, we have to compare this line with this line, and this line is x minus theta c t, and this line is x minus v t. So comparing them, we find that v by c is approximately equal to theta for small v and small theta. So we have got a physical interpretation of this parameter theta, but only for small values of v. Now we have to ask the question, what happens if v is not that small? V could be maybe half the speed of light or something. Then these approximations are not, this should not reduce to Galilean, and also this should not be legitimate. Okay? So for this, we have a very simple way to fix the problem. If v by c is not less than 1, then if we identify cosh and sinh with these things, then we find that cosh squared theta minus sinh squared theta is coming out to be 1 minus v by c squared. This is what we neglected when v was small. Now we are putting it back. Okay, we are still assuming that theta is somehow that this transformation is somehow true, but we are seeing that obviously this is false because this is not equal to 1. But cosh squared of theta and minus sinh squared of theta is always 1 for all theta. So we learn how to repair our guess. We can repair our guess by simply putting in a factor called gamma here, and we'll fix gamma so that cosh squared minus sinh squared is back to being 1. And when we do that, we find that, so now let's see what the transformation looks like. So x prime was is gamma x minus vt, and this should also be equal to cos theta x plus theta ct. And now you see that gamma must be some function of v, which I don't know, and I have to fix it so that cos squared minus sin squared remains 1 for all theta, not just small. And that means that cos squared theta minus sin squared with this identification is simply gamma squared 1 minus v squared by c squared, and so this has to be 1. And with that we are finally done. So this means that gamma is 1 over square root of 1 minus v squared by c squared, and the transformation between two frames, which is compatible with constancy of speed of light, then becomes x prime equals gamma x minus v by c. It's convenient to write it this way, but it's just vt, and t prime also becomes gamma minus v by c x ct prime plus t. And these you should recognize are nothing, ct are nothing but the Lorentz transformations, which you have memorized, I'm sure. If you divide c from everywhere, you'll see that this is gamma x minus vt, and this is t minus v by c squared x. It's exactly the Lorentz transformations. So what's important here is to realize that there are two steps. One is the mathematical step to make the speed of light the same in two frames, which just gives us constraints on four constants a, b, c, d. The second step is to identify a, b, c, d correctly with the velocity of the moving frame. It was that second step which some of you might have found confusing. We started by taking v small, and we found that theta and v should be somehow closely related. But then we realized that if v gets larger, then this cos squared minus sin squared relation just fails. So therefore we have to modify our assumption of Galilean relativity, and we just modified by putting a v dependent function in front, and it works very nicely, and we get an answer. So we have derived this. I don't know if your previous courses on special relativity have derived the Lorentz transformations, or just told you that Lorentz says these are his transformations and Einstein agrees, so you also have no choice but to agree. Is that what you were told, or you were shown these steps? Okay, I don't know, there seems to be some silence. Which one?
Not shown these.
Okay, but these are the steps. As you can see, there's no way out. This is how it is. End of the discussion. That's a beautiful thing about physics. When you get the principles, when you state the principles precisely, the results have no choice but to follow. Okay, so what more do we want to say? We are out of time, and I definitely don't want to take away your lunch. Just give me 1 more minute to wind up. Last comment, which is very important. Give me a minute, please. Is that v by c equals tan hyperbolic of theta. I'll use this next time. If you just take the Lorentz transformations and divide them, you'll get that v by c, or just rewrite these, compare these with these, you'll find that v by c is tan hyperbolic of theta. This of course agrees with theta for small theta. But this is a very important formula, because theta is a new way to measure the velocity of one frame relative to another. It's the mathematical way, but actually particle physicists who do accelerator experiments use this variable and not that variable. Okay, and it's called the rapidity. And next time we'll start with this equation. So this is what I wanted to finish today by saying. Okay, is it clear how this comes about? Okay, you could just go over your own notes for this thing, and you will find that this is just by dividing the expressions for sinh and cos, you'll get this. Okay, see you on Wednesday. Remember, again, Wednesday, but I don't know what is the room. I'll have to find out and I'll announce it. Wednesday 2 p.m. You should all be free because it's the same group as this. this class.